What if the universe around us isn't evenly filled, but hollow where we stand? Tonight, on Fall Asleep to Astronomy, we drift into a quiet idea scientists are now taking seriously, that Earth may sit inside a vast, under-dense bubble of space, an invisible pocket that subtly bends our measurements and gently reshapes how distant galaxies seem to move. It sounds strange, almost lonely, yet there's a calm beauty in imagining the cosmos holding a secret shape around us. If this kind of soft wonder feels right to you, a quiet, like and gentle subscribe, help others find their way here. For now, settle in, and we'll follow the dim outline of this cosmic bubble, unhurried and warm. Right now, you can imagine yourself drifting through an enormous hollow in space, a bubble about 2 billion light-years wide, where roughly 1/5 of the usual matter is missing. Astronomers have traced its outline using faint echoes from the birth of the universe, the relic glow of the Big Bang. The evidence is strong, something like 100 million times more likely than a simple coincidence. This great, under-dense shell wraps around Earth, the Milky Way, and every familiar star you have ever looked up at in the night. It has been there all along, hiding in plain sight, quietly tugging at our measurements and slipping into our equations. Because of it, the universe turns out to be stranger and perhaps a little more delicate than we once believed. To feel why this emptiness matters, you can picture how scientists measure the stretching of space itself. They watch distant galaxies drift away, like small lanterns carried along an invisible current, and from their speed, they infer how fast the universe expands, a value called the Hubble constant. They do this in two very different ways. One method looks back to when the universe was only a few 100,000 years old. Light from that time, the cosmic microwave background, still bathes all of space. In its tiny temperature ripples, scientists read the physics of the infant cosmos and infer an expansion rate of about 67 kilometers per second per megaparsec. Another method does not look so far away. It builds a ladder of distances using nearby stars and bright stellar explosions called supernovae. Step by careful step, this ladder leads to a higher expansion rate, around 73 kilometers per second per megaparsec. The gap between 67 and 73 may sound modest, but for cosmology, it is like two finely tuned clocks that refuse to tick in unison, even as you check them again and again. For years, researchers have polished both approaches, reduced uncertainties, and questioned every assumption. Instead of fading, the disagreement has sharpened. Nobel laureate Adam Rees has said that the more precisely we measure, the more stubborn the tension becomes. It no longer looks like a simple mistake in the data. When the James Webb Space Telescope brought its sharp infrared vision to the problem, it did not make the numbers converge. It confirmed that the difference is real. That leaves us with a strange possibility. Either the early universe did not behave exactly as our equations say, or our measurements of the nearby universe are being skewed by something subtle and local. Or perhaps the story is even more surprising than that. This puzzle is known as the Hubble tension, though tension sounds almost too gentle. For many cosmologists, it feels closer to a quiet crisis. Our best overall picture of the cosmos, the lambda cold dark matter model, has described so much so well. It explains how galaxies grow from tiny seeds, why the chemical elements appear in the proportions we see, and how the temperature of the cosmic microwave background changes across the sky. Yet this same trusted framework cannot bring those two expansion rates into harmony. Statistically, the The disagreement has passed the so-called 5 sigma threshold. That is a careful way of saying there is only about a 1 in a million chance that the mismatch is just random noise. For roughly a decade, many hoped that better instruments or new data would gently pull the two numbers together. Instead, every fresh observation has deepened the divide. So what could possibly make the universe appear to expand at two different speeds? One possible answer lies in the way the early cosmos rang like a silent bell. Before there were stars or galaxies, even before simple atoms existed, the universe was filled with a hot plasma, a mixture of light and charged particles moving together as a single fluid. In that young cosmic ocean, gravity pulled matter inward, while pressure pushed it back out. Imagine a still pond, disturbed by countless pebbles dropped all at once. Ripples spread, overlap, and weave into complex patterns. The early universe behaved in a similar way, but the ripples were not in water. They were sound-like pressure waves propagating through the plasma at more than half the speed of light. No one could have heard them. They were not notes in air, but gentle compressions and rarefactions in the density of matter and radiation spread across immense distances. Slightly denser regions began to collapse under their own weight, but radiation pushing outward resisted, creating rhythmic pulses, shells of compressed and thinned plasma expanding like invisible bubbles. As these waves traveled, they carried ordinary matter along. Dark matter, interacting mainly through gravity and not with light, tended to stay closer to the original centers, gathering quietly into unseen clumps, while the luminous plasma flowed in and out. After about 380,000 years, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. In that moment, light was freed to move without constant scattering. The pressure that had been driving the waves vanished, and the ripples effectively froze in place. It is like a pond surface turning to ice midway through a wind. The waves, instead of fading, would be locked in as patterns in the frozen sheet. In the cosmos, those frozen waves became slight over and under densities in matter. Today, after billions of years of expansion, we still see their imprint in the large-scale arrangement of galaxies. Astronomers call these patterns baryon acoustic oscillations. They act as a kind of standard scale. Back when the universe first cooled, the typical size of a wavefront was of the order of a few 100,000 light-years, roughly 450,000 light-years. Over about 13.8 billion years of expansion, that scale has stretched to roughly 500 million light-years. When astronomers catalog millions of galaxies and count how many appear in pairs separated by different distances, they find a subtle bump at that scale. There is a small but consistent excess of galaxy pairs separated by about 500 million light-years, compared with slightly smaller or larger separations. This pattern appears in many directions and surveys, like a faint recurring note in the cosmic song. What makes this ruler special is that its true length is set by well-understood physics in the early universe: how fast waves moved in the plasma, how long it took atoms to form, what the temperature and density were back then. Because those conditions are encoded in the cosmic microwave background, we can calculate how long the ruler should be. And because we can see this preferred separation in galaxy maps at different cosmic ages, we can track how the universe has swelled over time. But a quiet question lingers. What if the ruler does not look the same everywhere? What if living in a particular kind of region bends our view of this pattern just enough to mislead us? When astronomers count galaxies in all directions, looking deeper and deeper, they find something odd. Inside a sphere roughly 1 billion light-years around us, there appear to be fewer galaxies than expected. Light arriving from regions farther out, at distances around 1.5 billion light-years, seems to be about 1/2 brighter per unit volume than light from our immediate surroundings. It is like living in a sparse suburb. When you look toward the horizon, most of the glow comes not from nearby houses, but from distant cities. Our cosmic neighborhood seems to be the quiet outskirts. The crowded downtowns of galaxies lie farther away. Hints of this pattern first became clear when astronomers Ryan Keenan, Amy Barger, and Lennox Cowie analyzed tens of thousands of galaxies from several sky surveys. Mapping their distribution, they noticed that the density of matter appeared to decline toward our position. Their work suggested that the region around us might be between roughly 15 and 50% less dense than the cosmic average. They named this vast underdense zone the KBC void, from the initials of their surnames. Some prefer to call it the local hole, a name that sounds less technical, but perhaps more unsettling. In cosmic terms, this void is immense. It stretches roughly 2 billion light-years across, or about 600 megaparsecs in the language astronomers use. By comparison, our local group of galaxies, including the Milky Way and Andromeda, spans only around 10 million light-years. The void is about 200 times wider than this small island of galaxies we call home. Yet a void is not true emptiness. It is simply a region where galaxies are scarcer. In a typical volume of the universe, you might expect to find hundreds of galaxies. In a void, perhaps only a fraction of that number. The matter has not vanished. It is just spread more thinly. Our particular void still holds the Milky Way, the local group, and much of the Laniakea supercluster, a giant structure containing far more than 100,000 galaxies tied together by gravity. Even so, when you compare it to the overall cosmic average, we are living in a kind of enormous, quiet desert. The Milky Way sits not at the very edge of this desert, but somewhat near its center, within a few 100 million light-years of the middle. That position is important. If we were near the boundary, we would see the sky heavily crowded in one direction and more empty in the other. Instead, the underdensity appears fairly uniform across most of the sky. Different kinds of surveys converge on this same picture. Observations in visible light, in infrared glow, in X-ray emission, and in radio waves all tell a similar story. Fewer galaxies nearby, more at greater distances. The large-scale galaxy map seems to whisper the same message no matter how we listen. So how could such a huge, underdense region have formed? And what does living inside it do to our view of the universe? Imagine removing 1/5 of all matter around you. 1 out of every 5 galaxies gone. 1 out of every 5 clumps of dark matter erased. That is roughly what it means to inhabit the KBC void. A 20% deficit may sound modest, but across volumes this large, it represents a vast missing mass. The force that feels this loss most keenly is gravity, the quiet glue of the cosmos. Where matter is dense, gravity digs deep, wells in the fabric of space-time, pulling in yet more material and growing denser still. Where matter is sparse, gravity is weaker. Material tends to drift away toward richer regions, like dust rolling off a hill into distant valleys. Over billions of years, voids become emptier, while dense regions become more crowded. The 20% shortfall in the KBC void leads to 2 important effects. First, in terms of gravitational potential, underdense regions act like hills rather than valleys. Galaxies and gas naturally roll away from the center toward denser surroundings. The void gently pushes matter outward. Second, The expansion of space inside such a region is less hindered by gravity. With less mass to slow it down, space can stretch a little more freely. To observers living inside the void, nearby galaxies will appear to recede slightly faster than they would if the region had average density. When we measure the recession speeds of galaxies close to us, we are therefore sampling the expansion rate inside this special environment, not the perfectly averaged universe. It is a bit like trying to judge Earth's climate from the middle of Death Valley. Your thermometer will record higher temperatures than the global mean, not because the equations of climate are wrong, but because you are standing in an unusually hot place. Cosmologists worry that we may be doing something similar with the cosmic expansion. And yet, a difficulty remains. The lambda cold dark matter model says that when you look on very large scales, the universe should be remarkably uniform. Small variations in density are expected. Galaxies form groups. Groups assemble into clusters, and clusters into superclusters. But if you average over regions hundreds of millions of light years across, the density should settle close to the same value in most places. A void spanning about 2 billion light years, with a density roughly 20% below average, does not fit comfortably within that expectation. According to the standard model, the chances of such a structure appearing purely from random early ripples are extremely slim. Some calculations suggest odds on the order of 1 in a billion. Yet the sky keeps repeating the same quiet message. However we measure it, the region around us is underdense. Different teams, with different telescopes and methods, keep finding the same pattern. So we face an odd choice. Either we are improbably unlucky, living in a very rare patch of the cosmos, or the simple picture inside our cosmological model is missing a piece. There is also a third, more unsettling possibility. Perhaps what looks rare in our equations is actually common, and the universe is more lumpy, more clumpy than our models have allowed. Voids are not fixed holes carved into space. They evolve, and when a void evolves, it tends to empty out. The idea is simple. Inside a void, the density is a little lower than average. Around it, the density is a little higher. Those denser walls have stronger gravity. Their pull reaches into the underdense region and tugs on everything inside. Galaxies near the edge feel this tug most strongly. They start drifting toward the richer outskirts. As they leave, the interior becomes slightly emptier, which deepens the contrast. A deeper void means a stronger pull from outside, which encourages still more matter to flow outward. Over cosmic time, this becomes a runaway process. The void slowly swells and hollows. Cosmologists call this the evacuation of a void. It has been underway since the universe was young. Every billion years or so, matter slides from sparse regions into denser structures. We see whole swarms of galaxies moving together at several hundred kilometers per second across distances of hundreds of millions of light years. These are not random jitters. They are broad, coherent streams, like wide rivers of galaxies flowing down an invisible gravitational slope. The Milky Way is caught in this flow as well. Calculations suggest that our galaxy is moving outward from the center of the local underdensity at a few hundred kilometers per second, on the order of several 100,000 miles in an hour. We are, in a gentle and patient way, already drifting away from the deepest part of the bubble that surrounds us. This quiet motion has serious consequences for how we measure the expansion of the universe. When astronomers point a telescope at a distant galaxy and determine its redshift, they are really seeing two effects blended together. First, there is the stretching of space itself. the general expansion that carries galaxies apart. Second, there is the galaxy's own motion through space as it falls toward denser regions. Inside a void, most galaxies are moving outward from the center toward the walls. That means that, in almost every direction we look, the galaxies we study have an extra bit of redshift on top of cosmic expansion. Their light has been stretched, both by the growth of space and by their fall down the gravitational hill. The total shift we measure is a little larger than expansion alone would give. When we use these nearby galaxies to estimate the Hubble constant, we are therefore working with inflated redshifts. The expansion rate we infer looks faster than the true cosmic average. Indranil Banik, at the University of St. Andrews, has modeled this effect in detail. His calculations suggest that a void like the KBC region could increase the locally measured Hubble constant by about 11%. The way the numbers fall together is surprisingly neat. If the true expansion rate is around 67 kilometers per second per megaparsec, and the void's dynamics add roughly an 11% upward bias, the apparent rate becomes close to 74 kilometers per second per megaparsec. That is essentially what local measurements report. There is, however, an important condition. This explanation works cleanly only if we are relatively near the void's center. If Earth were close to the edge, the effect would be lopsided. In some directions, the added redshift would be strong. In others, it would be weaker. Instead, observations show a fairly uniform enhancement across the sky that places us somewhat uncomfortably within a few 100 million light-years of the middle. The odds of that feel suspicious. Living in a very large, very underdense void already seems unlikely. Living near its center seems even more so, unless such voids are more common than we think, or something about their centers makes them more favorable for galaxies and observers. This kind of reasoning, asking what sorts of places are most likely to host beings who can ask the question, is called anthropic reasoning. It makes many scientists uneasy, but the universe is not obliged to soothe our preferences. A gentler picture is to imagine yourself on a moving walkway in an airport. People walking toward you appear to approach faster than they would on solid ground because the walkway's speed adds to theirs. If you tried to measure their walking speed without accounting for the belt, you would overestimate. Measuring cosmic expansion from inside a void is similar. The outward flow of galaxies adds its own motion on top of the general stretching of space. Every measurement carries truth, but to understand that truth, we must know the context. When Henrietta Swan Leavitt discovered that the brightness of some variable stars is tied to how quickly they pulse, she gave astronomy a luminous ruler. Edwin Hubble used that ruler to measure galaxy distances and found that space expands. Later, Saul Perlmutter, Adam Rees, and Brian Schmidt used exploding white dwarf stars as beacons to refine those measurements and discovered that dark energy is accelerating the expansion. In each case, the assumption was that these signals reflected universal behavior, not local quirks. Inside the KBC void, though, our neighborhood is not entirely typical. Space is genuinely expanding here, but the way it expands is slightly distorted by the underdensity. It is like trying to describe Earth's climate from a single weather station. If your station is in a desert, you might conclude that the planet is hot and dry. If it is on an icy plateau, you might decide that the world is cold and barren. Both stations are honest. Neither tells the whole story. The same is true for cosmic redshift. Light leaves a distant galaxy and begins its long journey toward us. Along the way, the fabric of space stretches, lengthening its wavelength. That stretching is cosmological redshift. Inside a void, the galaxy is also falling down a gravitational hill, adding a second contribution to the stretching. Our instruments cannot easily tell which part comes from expansion and which part from motion, so we treat all of it as expansion and feed it into our equations. The result is a Hubble constant of about 73 instead of about 67. Banach frames this in terms of gravitational potential. On the cosmic landscape, dense clusters and superclusters are valleys. Voids are hills. Galaxies roll from hills toward valleys. That motion is not expansion, it is falling. But from the perspective of light, both falling and expanding stretch wavelengths in similar ways. Redshift alone cannot distinguish them. The only way to tease them apart is through statistics. By measuring many galaxies in many directions and at many distances, patterns emerge. The evacuation of a void introduces a systematic bias. Local measurements taken inside the underdense bubble tend to be slightly inflated. Farther out, beyond the void's edge, the bias fades. This is exactly what observations suggest. The Hubble tension appears at low redshifts, where our measurements probe the relatively nearby universe that includes the KBC void. At higher redshifts, where we look deep into space and back in time, sampling regions far beyond our local bubble, the tension melts away. The cosmic microwave background, which comes from the entire observable universe at once, gives us the true average expansion rate. Local measurements tell us how space behaves inside our bubble. Both are correct. They are simply answering different questions. Accepting this picture means admitting that we live in a somewhat special place, not special in a mystical sense, just statistically unusual. Our cosmic neighborhood does not perfectly mirror the cosmos at large. That makes cosmology harder. We cannot assume that what happens here is exactly what happens everywhere. We have to correct for local peculiarities when we read the sky. Some researchers resist this. They prefer to seek new ingredients in the cosmic recipe, an extra pulse of dark energy in the early universe, subtle modifications to gravity on very large scales, time-varying properties of dark energy, new kinds of particles that interact only in the dark sector. All of these ideas are possible. They are also more intricate, requiring us to extend or rewrite pieces of fundamental physics. The void explanation is simpler. It relies only on gravity, on variations in density, and on the motions those variations produce. No exotic forces, no new particles. Over the past 2 decades, a wide array of observations has quietly piled up in its favor. Galaxy redshift surveys, mapping 3-dimensional structure, measurements of how galaxies cluster at different epochs, detections of baryon acoustic oscillations at many distances, studies of bulk flows showing matter streaming toward denser regions. Each dataset hints at an underdensity around us. Together, they point to a single picture. We live in an underdense bubble. To test that picture, researchers compare 2 kinds of models. The first is the familiar one, where the universe is statistically uniform on large scales, described by the lambda cold dark matter framework and calibrated by the Planck satellite's measurements of the cosmic microwave background. The second is the same, but with one extra ingredient, a local void similar to the KBC region. They then ask which model better fits the actual data, especially the pattern of baryon acoustic oscillations. The answer is striking. The model that includes a void is found to be roughly 100 million times more likely than the model without one. In compact scientific language, That ratio is written as 10 to the 8th power. In ordinary terms, the evidence strongly favors the existence of a local void. For comparison, particle physicists typically require what they call 5 sigma significance, odds of about 1 in a few million, against chance to declare a discovery. The statistical support for the void surpasses that mark by a comfortable margin, and it does so not through a single fragile measurement, but by combining many independent lines of evidence. Of course, science does not deal in absolute proof. There is always room, at least in principle, for alternative explanations. Multiple, unrelated, observational biases that happen to align unusual behaviors of dark matter or dark energy. Subtle quantum effects on cosmic scales. These possibilities are not impossible. They simply appear less probable than the straightforward story in front of us. Some scientists object that, within the lambda-cold dark matter framework, voids as large and deep as the KBC region should be extremely rare. Finding ourselves in one feels like winning a cosmic lottery. But rarity is not the same as impossibility. Someone does win the lottery. Unusual star systems form, outlier galaxies exist, and if there is any way in which void centers are especially friendly to galaxy formation or to life, then observers would naturally find themselves there more often than random chance alone would suggest. For about a decade, the Hubble tension has been one of cosmology's most persistent headaches. 2 careful methods, 2 careful answers, differing by roughly 9 kilometers per second per megaparsec. Careers have been devoted to tracking down the discrepancy. New instruments have been built to probe it. Theorists have proposed whole menageries of new physics. And yet, all that elaboration may not be needed. The presence of a large, underdense bubble around us offers a quieter, more elegant way through the puzzle. It explains the mismatch, using only the familiar language of gravity and structure. It asks us to accept that our neighborhood is unusual, but it does not demand that we rewrite the basic laws of the universe. The void provides an elegant solution that requires no new physics. To untangle this quiet disagreement about how fast the universe is expanding, it helps to gently ask what each method is really measuring. One method listens to the cosmic microwave background, the ancient light released when the universe was only about 380,000 years old. That glow arrives from every direction at once, bathing us in a faint shell of memory that samples almost the entire observable cosmos. In its tiny temperature ripples, changing by only about 1 part in 100,000, astronomers read the young universe's density, its ingredients, and how quickly it was beginning to stretch. They take those ripples and feed them into the equations of the lambda-cold dark matter model, then let the mathematics run forward for roughly 13.8 billion years. From hot plasma to galaxies and clusters, the calculation follows the universe's growth and finally predicts today's expansion rate, about 67.4 kilometers per second per megaparsec. That number is a global average, a description of the universe as a whole, smoothed over everything. The other method stays much closer to home. It uses a distance ladder built from living stars and dying ones. It begins with Cepheid variable stars in nearby galaxies, gentle lights that pulse in a steady rhythm. The length of that rhythm reveals their true brightness. Compare true brightness to how faint they look, and you learn their distance, almost like judging how far away a candle is from the size of its flame. Once those distances are known, the same galaxies host Type 1, a supernovae. These explosions from white dwarf stars reach almost the same peak brightness every time. Using the Cepheids as anchors, astronomers calibrate that brightness and turn Type 1, a supernovae, into standard candles. Then the ladder reaches farther. They find such supernovae in more distant galaxies, where individual Cepheids are too faint to see. The supernovae's faintness tells us how far away those galaxies are. Their redshift tells us how fast they are receding. Distance and velocity together give a direct estimate of the Hubble constant. This local ladder gives a higher value, about 73.04 kilometers per second per megaparsec. At first glance, it feels like two careful answers to the same question. But there is a quiet asymmetry in what each method samples. Cepheid variables can only be measured reliably out to around 100 million light-years. The Type 1, a supernovae used for calibration, reach perhaps 2 to 3 billion light-years. All of that distance range lies within the KBC void, the large, underdense bubble surrounding our part of the cosmic web. So the ladder does not measure the expansion of the entire universe. It measures the expansion inside the void. The cosmic microwave background method, by contrast, listens to light that has crossed almost the whole observable cosmos. Its 67.4 value is about the expansion averaged over everything. These are different quantities, one global, one local. You can imagine two scientists trying to measure average human height. One measures only people in a very tall country and finds an average around 183 centimeters. Another uses worldwide data and finds about 171 centimeters. Both are correct. They simply measured different populations. The Hubble tension is essentially that situation played out on a cosmic scale. The void offers a natural reason why the local value runs high. Inside an underdense region, there is less matter to slow the expansion. Outside, thicker walls of galaxies and clusters have stronger gravity and gently pull material outward. Galaxies slide away from the void's center toward its edges, adding their own motion on top of the overall stretching of space. Their light carries extra redshift, a little more stretching than pure expansion would produce. Indranil Banik and colleagues have modeled this for a void with the size and depth of the KBC region. Their calculations suggest that living in such a bubble can inflate the locally inferred Hubble constant by roughly 11%. Start with a true global rate, near 67 kilometers per second per megaparsec. Add about 11%, and you arrive close to 74 kilometers per second per megaparsec, almost exactly what the distance ladder finds. Some details still need refining. Astronomers want better maps of the void's exact size and density profile, and a clearer picture of how close the Milky Way sits to its center. Alternative ideas for the Hubble tension, early dark energy, small changes to gravity, and others need to be checked carefully against the same data. But the basic void mechanism is simple, and it makes testable predictions. If the void explanation is right, then measurements that reach beyond roughly 3 billion light-years into regions where density approaches the cosmic average should begin to see lower Hubble values drifting towards 67. The tension should fade at large distances. Bulk flows of galaxies should align with matter, streaming outward from the underdensity toward denser structures. In directions where the void is not perfectly spherical, the inferred expansion might show subtle directional differences. New surveys are designed to look for exactly these hints. The James Webb Space Telescope can spot Cepheid variables at greater distances, stretching the ladder farther beyond the heart of our bubble. The Vera Rubin Observatory will map billions of galaxies, tracing the filaments, clusters, and voids that make up the cosmic web. The Euclid mission will measure baryon acoustic oscillations, fossil sound wave patterns in galaxy clustering across much of cosmic history. showing how a standard ruler appears at many epochs. Together, they will quietly ask the universe whether our hollow neighborhood is enough to explain the mismatch. If the answer is yes, the Hubble tension may fade, not through revolutionary new physics, but through a humbler realization that where we live matters, and that measuring the universe from inside a void naturally tilts the results. We would not be sitting in a mystical center of creation, just in a statistically unusual patch of space that complicates our view. And the void itself? You cannot see it outlined in light. A void is defined by absence. Astronomers find it by counting what is there and noticing what is missing. One simple approach is to survey a large region of space and divide it into many identical three-dimensional boxes. In most boxes, you find similar numbers of galaxies. Some boxes are richer, hosting clusters and superclusters. Some are a little poorer. But when you find a connected chain of boxes that each contain far fewer galaxies than average, you have traced out a void. Early redshift surveys in the 1970s already hinted at this foam-like cosmic web, bright filaments of galaxies, knots where they cross, and wide dark bubbles between them. Later projects like the 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey, and all-sky infrared maps made the pattern clearer. As the data improved, the KBC region emerged as a particularly large hollow. In many directions, galaxy counts simply fall as you move inward toward the Milky Way. Counting positions is only one way of listening. Another is to watch how galaxies move. Every galaxy has two components to its motion: recession from the overall expansion of space, and peculiar velocity from local gravitational pulls. If you know a galaxy's distance, you can estimate how fast it should be receding from expansion alone. Compare that to its actual motion, and the difference is its peculiar velocity. Doing this for many thousands of galaxies reveals broad flow patterns. On large scales, galaxies tend to stream out of underdense regions and into denser walls and clusters. Catalogs of these cosmic flows show motions around us that match the idea of a nearby void. Galaxies near the inferred edges move outward faster than pure expansion would suggest, while those nearer the center drift more gently. The pattern fits an underdensity roughly 1 billion light-years in radius. Other techniques add quieter support: small distortions in the standard ruler of baryon, acoustic oscillations, faint imprints on the cosmic microwave background from photons crossing, changing gravitational landscapes, and subtle gravitational lensing signatures where light is bent slightly less than average as it passes through low-mass regions. Each method alone whispers the same hint. Together, they describe a local universe that is genuinely underdense. All the while, the cosmic microwave background continues to shine, a nearly perfect black-body glow with a temperature of about 2.725 Kelvin. Its tiny hot and cold spots mark regions that were slightly denser or slightly emptier in the early universe. Over billions of years, gravity amplified those seeds into today's clusters, filaments, and voids. From the pattern of those temperature ripples, missions like Planck and the Wilkinson Microwave Anisotropy Probe have inferred the universe's basic composition and predicted a present-day expansion rate, around 67.4 kilometers per second per megaparsec. Those predictions are robust and global. The puzzle only appears when we set them beside local measurements. And that puzzle is not a failure of the cosmic microwave background. It is quiet evidence that the conditions in our part of the cosmos are not perfectly average. That local space, shaped by a great underdense bubble, bends what we see just enough to make the universe's expansion look different from here. Some stars in the universe behave like sleepy cosmic lighthouses. Slowly, steadily, they swell and shrink, brightening as they expand, dimming as they contract. These are Cepheid variable stars, enormous yellow supergiants nearing the ends of their lives. Their pulses are not random. The longer the pulse, the brighter the star truly is. The shorter the pulse, the dimmer its real light. In the early 1900s, Henrietta Swan Leavitt noticed this pattern and quietly changed astronomy forever. She found that a Cepheid's pulsation period is tied to its true luminosity. Once you know that, the steps become simple in principle. You watch a Cepheid and measure how long it takes to complete one cycle of brightening and fading. That rhythm tells you how much light it is really emitting. Then, you measure how bright it appears from Earth. If a star that should be very bright looks faint, it must be far away. If it looks nearly as bright as its true power, it is nearer. The difference between true brightness and apparent brightness reveals distance. The relationship is precise and can be written down in clean mathematical form, even if the star itself is a swollen, restless sun. The hard part is not the math, it is finding the stars. Cepheids are rare. Only a few thousand live in our entire Milky Way, and in distant galaxies, individual stars blur together into soft smears of light. Seeing a single Cepheid in a galaxy tens of millions of light years away requires a sharp eye in space, like that of the Hubble Space Telescope, or something even better. Yet Cepheids are essential for building the cosmic distance ladder. They sit in a sweet spot, bright enough to be seen in nearby galaxies, but rare and distinctive enough to be picked out one by one. They link the very close distances we measure through parallax to the much larger scales where other methods must take over. For years, a project known as the supernova H0 for the equation of state, usually shortened to SH0ES, has been patiently watching Cepheids in galaxies where Type 1a supernovae have also appeared. Type 1, a supernovae are explosions of white dwarf stars, brief but astonishing events that can outshine entire galaxies. More importantly, their peak brightness is remarkably consistent. This makes them standard candles for measuring vast distances, but only once we know exactly how bright they truly are. That is where Cepheids become the bridge. You find a galaxy that hosts both Cepheid variables and the remnant of a Type 1, a supernova. You use the Cepheids to determine the galaxy's distance with high precision. That distance, in turn, tells you the true brightness of the supernova that exploded there. Do this in several galaxies, and you build a calibration for Type 1, a supernovae. You learn how luminous they really are, on average. Then you turn your gaze farther out. You look for Type 1, a supernovae in galaxies so distant that Cepheids are too faint to see at all. For those systems, you rely solely on the supernovae. Their apparent faintness gives their distance. Their redshift tells you how fast their host galaxies are receding. With many such galaxies, you can compute the Hubble constant. Adam Rees has led this work for many years. His team has measured well over 1,000 Cepheids in numerous galaxies and observed dozens of Type 1 supernovae tied to them. The precision is extraordinary, with uncertainties shrunk to a few percent. When the James Webb Space Telescope began operating, Rees and colleagues used it to test the entire ladder. James Webb sees in infrared light and has finer resolution than Hubble. It can peer through dust that might dim Cepheids and separate crowded stars more clearly. If earlier measurements had been confused by overlapping light or hidden dust, James Webb would show the problem. Instead, it confirmed the Hubble results almost perfectly. The locally measured Hubble constant remained near 73 kilometers per second per megaparsec. The tension with the cosmic microwave background did not fade. Some critics have wondered if Cepheid measurements still hide subtle systematic errors. Perhaps crowding affects brightness in ways not fully captured. Perhaps dust absorbs light more intricately than our models allow. Perhaps Cepheids in different galactic environments behave slightly differently. Researchers have tested these worries carefully. They have observed Cepheids in many kinds of galaxies, checked dust using several wavelengths of light, and searched for trends that could drag the Hubble constant upward. Nothing convincing has emerged. The measurements appear stubbornly robust, but there is a quiet, crucial limitation. Cepheids can only be measured out to a bit more than 100 million light-years. Beyond that, they are simply too faint. This means that every Cepheid used to calibrate Type 1, a supernovae, lives in the relatively nearby universe, and that nearby volume lies entirely inside the KBC void. In other words, all the Cepheids that anchor the supernova distance ladder are measuring expansion inside an underdense region. If the void causes local space to expand slightly faster than average, then Cepheids will faithfully record that faster rate. They are not wrong. They are just telling us about a special neighborhood. Type 1, a supernovae, can be seen much farther away, out to billions of light years. Some of those distant supernovae lie beyond the void's edge, but their distances are calibrated using nearby supernovae that sit in Cepheid-rich galaxies inside the void. If the local calibration is based on a region expanding faster than average, that local expansion rate quietly propagates outward along the ladder. This does not make the distance measurements useless. It makes them context-dependent. The method assumes that the expansion rate we measure nearby applies everywhere. If it does not, if we live in a patch of the universe that expands a little faster, then the distances inferred using that rate will be systematically biased when applied beyond our special region. The remedy is not to discard Cepheids or supernovae. They remain exquisite tools for mapping our corner of the universe. The remedy is to recognize their reach and their limits. They excel at revealing local structure and the expansion of our immediate cosmic neighborhood, but they cannot, by themselves, define the global average expansion. For that, we need methods that sample the universe more evenly, such as the cosmic microwave background and baryon acoustic oscillations at high redshift. Science grows on such disagreements, competing theories, conflicting measurements, unexpected outcomes. These are what push us forward. But there is a difference between healthy tension and something that feels like an existential crack. The Hubble tension crossed that line in the middle of the 2010s. Before then, the uncertainties on both sides were large enough that the different measurements could still overlap. A true Hubble constant, somewhere between roughly 67 and 73 kilometers per second per megaparsec, seemed plausible. It might be 70, it might be 72. It was hard to be sure. Then technology sharpened our view. The Planck satellite delivered cosmic microwave background data with astonishing precision. The Hubble Space Telescope gathered light from hundreds of Cepheids in dozens of galaxies. Supernova surveys cataloged thousands of explosions at many distances. The error bars shrank. The ranges no longer overlapped. By around 2018, the discrepancy had reached several sigma in statistical language, meaning the odds of it being a random fluctuation were small. By roughly 2019, the significance passed the 5 sigma mark, corresponding to odds of only about 1 in several million that the mismatch was just chance. In particle physics, 5 sigma is the threshold for declaring a discovery. In cosmology, A 5 sigma disagreement between fundamental measurements signals that something important is amiss. In response, theorists have explored a garden of new ideas. Perhaps there was a brief phase of early dark energy that altered the young universe's expansion and then faded. Perhaps dark energy itself changes its properties over time. Perhaps gravity behaves slightly differently on the largest scales than Einstein's equations predict. Perhaps extra, nearly invisible particles affected the early cosmos. Perhaps dark matter and dark energy interact in subtle ways. Each of these suggestions must be tested against many lines of evidence. The cosmic microwave background ripples, the large-scale distribution of galaxies, the abundances of light elements formed shortly after the Big Bang, gravitational lensing, cluster counts, and more. Most of the exotic proposals fix the Hubble tension only to break something else. The elegance of the lambda cold dark matter model lies in how well it matches many independent observations. Any modification that saves one problem but spoils 3 successes is hard to accept. On the observational side, experimental teams have scrutinized their instruments. Could the Hubble Space Telescope hide tiny calibration errors? Could the Planck satellite be slightly misreading the microwave sky? Could ground-based supernova surveys suffer from subtle atmospheric biases? Thousands of hours of checking have turned up nothing decisive. James Webb, with its superb vision, was expected by some to reveal flaws in the Hubble Cepheid data. Instead, it confirmed them. At that point, some researchers began to wonder if the issue was not in the instruments or the basic physics, but in one of our quiet assumptions. The cosmological principle, the idea that, on large enough scales, the universe looks roughly the same everywhere, has guided cosmology for a century. It grew out of the realization that Earth is not at the center of anything, that we orbit an ordinary star in an ordinary galaxy in a typical place. Letting go of that principle feels, to some, like a step backward. But science follows evidence, not comfort. If observations show that large-scale uniformity is only approximate, not exact, we must adjust our picture. The KBC void is precisely the sort of structure that forces this question. It is not a small, local quirk. It is a vast region, affecting a significant portion of the space we can observe, and we appear to live inside it. The coincidence bothers many people. Why would Earth sit in such a statistically unusual location? One answer, sometimes called anthropic, is that observers must exist somewhere, and perhaps voids offer slightly safer, calmer conditions for life. Lower density might mean fewer violent galaxy collisions, less intense radiation, more time and stability for complex chemistry to unfold. This is speculation, but it is not wild speculation. The void explanation is appealing because it asks for no new physics. Voids are already part of standard cosmology. Their behavior under gravity is well understood. They alter redshifts and apparent expansion in exactly the ways we observe. No new particles, no modified gravity, no mysterious bursts of early dark energy, just the same equations, applied carefully, with local structure included instead of ignored. Even with all this evidence, not everyone feels at ease with the idea that we live inside a great hollow in space. Some scientists find the void explanation strangely unsatisfying. If the KBC void is real and important, does that mean the lambda cold dark matter model is still right, just incomplete in its details? Or does it mean our standard picture of the universe needs to be adjusted to allow for larger, rarer structures than we expected? The answer, as usual in cosmology, is soft and subtle. The lambda cold dark matter framework still does an impressive job describing the average evolution of the universe. It predicts the pattern of the cosmic microwave background remarkably well. It explains how matter, on the whole, clumps into filaments, clusters, and voids, but it may be a little too optimistic about how smooth things become on the largest scales. Our view of structure formation is shaped by computer simulations, and those simulations have limits. They cannot model the entire observable universe at high resolution. Instead, they follow the growth of structure in smaller, representative boxes of space, and then infer how often big features should appear. If genuinely huge voids like the KBC region are rare, they might not show up in typical simulation boxes at all. We could be missing them, not because the theory forbids them, but because our numerical experiments simply did not see one. It might be that voids as large as the KBC region are improbable, but not impossible, or that our understanding of how structures grow has small, systematic imperfections that only become obvious when you stretch them across billions of light years. Either way, resolving the Hubble tension will not come from a single spectacular observation. It will come from stitching together many quiet threads. We will need galaxy surveys that trace the void's true extent, measurements of bulk flows that follow the motion of matter across hundreds of millions of light years, baryon acoustic oscillations measured in different regions to see how expansion behaves in various environments, supernova distances that reach well beyond the void's edge. All of these are in motion now. Within about a decade of careful observing, the sky will tell us whether the void solution holds its ground. If it does, what we once called a crisis will gently dissolve. If it does not, the mystery will only deepen. For a moment, let your mind rest on the scale involved. The KBC void spans roughly 2 billion light-years from one side to the other. Light, traveling at its steady speed, would take 2 billion years just to cross it. In the language astronomers use, that is, about 600 megaparsecs. Set that beside familiar things. The Milky Way's disk is only about 100,000 light-years across. The void is roughly 20,000 times wider. The local group, the small family of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller companions, stretches to perhaps 10 million light-years. The void is about 200 times larger than that. Even Laniakea, the supercluster that is our galaxy's broad gravitational home, spans around 500 million light-years. The void is still about 4 times wider. This is not a small quirk in the map. It is one of the largest structures we know about. Other enormous voids exist. The Botes void, discovered in the early 1980s, spans a bit over 300 million light-years and was poetically nicknamed the Great Nothing. The Eridanus supervoid reaches close to 1.8 billion light-years across. The KBC void stands alongside these giants, but there is one crucial difference. Those other voids are things we look at from the outside. The KBC void is something we look out from. We are inside it. That makes measuring its dimensions especially difficult. It is like standing in the middle of a forest and trying to say exactly where the forest ends. You can count trees around you. You can notice when they thin out, but tracing the true boundary requires surveying enormous areas and studying how the density changes with distance. Cosmologists do the same thing with galaxies instead of trees. They divide space around us into concentric shells at increasing distances. In each shell, they count how many galaxies appear and compare that number to what a typical region of space should hold. At some distance, the counts begin to rise toward the cosmic average. That rise marks the edge of the void. Current measurements suggest that in most directions, the KBC void's edge lies at around 1 billion light-years from us, but there is room for uncertainty. In some directions, it might be closer to 800 million light-years. In others, perhaps 1.2 billion. Voids are not perfect spheres. Their boundaries are shaped and dented by the surrounding filaments and clusters. On one side, a structure called the local sheet, a flattened concentration of galaxies that includes the Milky Way, acts as one boundary wall. On the opposite side, other superclusters close the far edge. Even the center of the void is not pinned down exactly. Early estimates place it within a few 100 million light-years of the Milky Way, but finding the precise center requires mapping the full three-dimensional density field. Galaxies in all directions, out to several billion light-years. Surveys like the Sloan Digital Sky Survey and the 2-micron All-Sky Survey have done much of this work, but gaps remain. Dust in our own galaxy hides some parts of the sky. Limited observing time has left others undersampled. New projects will gradually fill those shadows. Despite these uncertainties, one message is clear. The void contains significantly less matter than average. Estimates suggest between about 15 and 50% below the cosmic mean, depending on where you look. Near the center, the deficit may be closer to 40%. Near the edges, perhaps nearer 20%. This gradient is not just a curiosity. It controls how strongly the surrounding structures pull on the interior and how much the void can distort our measurements of expansion. A steeper gradient means stronger outward flows and a larger impact on the Hubble constant. And yet, for all its emptiness, the void is far from truly empty. It holds the Milky Way and Andromeda and their smaller companions. It contains much of the Laniakea supercluster, with its hundreds of thousands of galaxies. Compared to a typical region of that size, though, it is underpopulated by perhaps 1/5. You can picture it as a city where every fifth building is missing. The streets still exist. People walk, lights glow, traffic moves. But if you compare it to a denser city nearby, this one feels noticeably open and airy, with patches of space where you might expect more towers. That is the KBC void, a cosmic city that works, just a little more spacious than the average. How does such a hollow come to be? In the standard cosmological story, the universe begins almost perfectly smooth. Tiny quantum ripples during inflation. The very early episode of rapid expansion plants small differences in density, at the level of roughly 1 part in 100,000. Some regions start with slightly more matter, some with slightly less. Over time, gravity amplifies these differences. Denser patches attract extra material and grow heavier. Underdense patches lose material to their neighbors and grow emptier. This slow drift is called gravitational instability, and it is the basic engine behind all large-scale structure. In the first few 100 million years, the densest spots collapse into the first stars. Those stars gather into small protogalaxies. Protogalaxies merge into larger galaxies. Galaxies fall together into clusters. Clusters string themselves along filaments. Between those filaments, the spaces that started slightly underdense stretch into voids. If you could look down on the universe from outside, it would resemble a foam of soap bubbles. Galaxies trace the thin walls. Voids fill the interiors. This pattern emerges naturally from gravity working on the initial fluctuations. But voids do not freeze once they form. Young voids still contain plenty of galaxies scattered through their interiors, slowly drifting outward. Over billions of years, gravity from the surrounding filaments pulls more and more material toward the walls. The void's interior gradually empties. By midway through the universe's life, a large void grows bigger and more pronounced. By the present age, about 13.8 billion years voids occupy most of the universe's volume, perhaps 80% or more, but contain only a minority of its matter, around 20%. They are underdense, but not totally evacuated. The KBC void seems to be a mature example. A large, long-lived hollow that has been developing for most of cosmic history. Growing a void this large in the lambda-cold dark matter picture requires starting from an unusually broad initial fluctuation. Random quantum jitter during inflation can, in principle, produce structures on many scales, but the biggest ones should be rare. That is the tension inside the tension. The void might solve the Hubble disagreement, yet its very existence presses back on the model that made our earlier predictions. Some alternative theories of gravity and dark matter find it easier to produce large voids. Modified Newtonian dynamics, often shortened to MOND, changes how gravity behaves at very low accelerations. In some versions, this can speed up structure growth on certain scales. Hot dark matter models with extra neutrino species affect how small and large structures form. In such frameworks, immense voids like the KBC region might appear more naturally. Whether standard lambda-cold dark matter or some adjusted version ultimately gives the best account is still an open question. What is not in doubt is that voids themselves form quite naturally from tiny beginnings, grow through well-understood physics, and become expected features of any universe where gravity slowly exaggerates small differences. The Milky Way does not sit alone in this picture. Our galaxy is part of a flattened structure called the local sheet, a kind of cosmic pancake extending for hundreds of millions of light years in two directions and relatively thin in the third. The local sheet contains multiple galaxy groups, the local group, the Maffei group, and others, each a small family of galaxies bound together on larger scales. These groups share a common motion, flowing in response to the gravitational pulls of nearby clusters and voids. The local sheet marks one of the boundaries of a smaller emptiness known as the local void, which itself sits inside the larger KBC void. You can think of nested shells, the vast KBC hollow on the largest scale, the local void as a smaller bubble within it, and the local sheet as one of the denser walls that separate these underdensities from richer structures beyond. Matter that once lay in the interior has been drawn toward that sheet over billions of years, piling up into a thin, wide layer. Measurements show that the local sheet is moving away from the center of the local void at a few hundred kilometers per second, a clear sign of void evacuation in action. The entire structure, containing billions upon billions of stars, is slowly sliding away from emptiness. Over long enough timescales, different parts of the sheet will stretch and drift, tugged by neighboring superclusters. One day, it may not exist as a coherent sheet at all. For now, though, it serves as a gently sloping boundary. On one side, the low-density piece of the void. On the other, regions of more typical or higher density cross from the void side to the far side, and galaxy counts rise smoothly. The transition is not a sharp wall, but a gradual thickening across tens of millions of light years. This asymmetry matters. If astronomers looked only in a few directions, they might have missed the void entirely. Only by surveying the sky nearly all around us does its shape emerge, and through all of this, one quiet fact remains. Our galaxy is not just circling the center of the local group. The whole local group of galaxies is not sitting still in space. It is drifting together as part of the local sheet, sliding gently away from the center of the nearby void. We are being carried along with it, like leaves caught in a wide, slow river. That motion matters whenever we try to measure how fast the universe is expanding. When we look at a distant galaxy and measure its redshift, we are really comparing its motion to ours. But our own motion already includes this evacuation flow, the way the local sheet is gliding away from the void. If a galaxy lies roughly in the direction we are moving, its light can look a little less redshifted than pure expansion would suggest, even slightly blue-shifted in extreme cases. If a galaxy lies in the opposite direction, its light appears a bit more red-shifted than expansion alone would produce. Over the whole sky, these effects partly wash out, but if we sample some directions more than others, a quiet bias survives. To correct for this, we need to know how fast we are truly moving through the universe. The cosmic microwave background gives us that answer in a very gentle way. Because we are moving relative to this ancient light, we see it slightly hotter in the direction we are heading and slightly cooler behind us. This simple dipole pattern tells us that the local group is moving at about 630 kilometers per second relative to the cosmic microwave background rest frame. That speed is the sum of many layers. The Milky Way drifting within the local group, the local group moving within the local sheet, the sheet itself flowing in response to larger structures like the Laniakea supercluster and the surrounding void. Untangling how much of our motion comes from each layer requires mapping the mass around us in detail and measuring the peculiar velocities of many galaxies. As we refine the shape and depth of the void, these corrections become more accurate. The numbers involved are almost dizzying. Earth orbits the Sun at roughly 67,000 miles in an hour. The Sun orbits the center of the Milky Way at close to 490,000 miles in an hour. The Milky Way moves within the local group at, on the order of 200,000 miles in an hour. And on top of all that, the entire local group is sliding away from the local void at roughly 600,000 miles in an hour, around 250 kilometers per second. Every second, our galaxy drifts about 250 kilometers farther from the void's center. In an hour, that is close to 900,000 kilometers. In a day, more than 20 million kilometers. In a year, many billions. None of that is due to the stretching of space itself. It is motion through space, pulled and pushed by gravity and the lack of it. Cosmic expansion is something different. When space expands, galaxies recede from one another because the fabric in between stretches. They do not need to move through that fabric. Peculiar velocities, by contrast, are real journeys. Galaxies sliding down gravitational slopes, falling toward dense clusters, or being pushed outward from under-dense hollows. A void behaves somewhat like a region of negative mass, not truly repelling, but creating a gravitational hill that everything nearby rolls off. Our net motion is read from the dipole in the cosmic microwave background, but knowing that total speed is only the first step, astrophysicists then try to decompose it into pieces. Part comes from our orbit within the local group, part from the entire group's motion within the sheet, and part from the sheet's flow out of the void and toward distant attractors. They do this by measuring peculiar velocities of tens of thousands of galaxies. Galaxies that share our motion belong to the same flow. Those that move differently respond to other structures. Catalogs of these velocities show that the local void contributes roughly a few hundred kilometers per second to our total speed. Even if it is not the largest flow in the universe, it is important because we are directly riding it. Every redshift we measure is taken from the vantage point of a galaxy that is actively fleeing an underdense region. All of this has to be peeled away as best we can to uncover the true expansion rate beneath. And yet, even when we correct for our motion, the void's influence does not vanish entirely. The underdensity itself changes how space expands in our neighborhood, making the local Hubble rate slightly higher than the cosmic average. Peculiar velocity and modified local expansion are woven together, and disentangling them requires detailed models of void dynamics. Those models exist, but they depend on quantities we are still learning: the void's exact radius, how sharply its density rises toward the edge, exactly where we sit within it. Uncertainties in those ingredients become uncertainties in our corrections. As surveys grow wider and deeper, and as we gather more velocity data, that picture will sharpen. For now, we can be certain of one thing: our flight from the void is real, measurable, and it quietly colors every measurement of the universe's expansion. From here, the story drifts back in time to an era before galaxies, before stars, before even atoms. In those early hundreds of thousands of years, the universe was not silent. It rang with a kind of sound. There was no air, no wind, no familiar noise. Instead, there was a hot, dense plasma, a mixture of protons, electrons, and photons locked together. This mixture behaved like a fluid. In regions that were slightly denser, the pressure was higher. That pressure pushed outward, while gravity pulled matter inward. The tug of gravity and the push of pressure set up vast oscillations, like a cosmic spring bouncing around its equilibrium. Imagine pressing on a spring, letting it go, and watching it overshoot on the other side. The early universe did that everywhere at once. Slight overdensities collapsed a bit under gravity, then rebounded as pressure pushed back, then fell inward again. These cycles sent pressure waves rippling outward from each initial fluctuation. They were not sound in the way our ears understand, but they were acoustic waves all the same, alternating compressions and rarefactions, traveling through the plasma at a significant fraction of light speed. Normal matter and photons participated in these waves, but dark matter did not. Dark matter does not feel pressure from light. It responded only to gravity, quietly sinking toward the centers of the original fluctuations and staying there. The result was a layered structure, dense clumps of dark matter at the original centers, surrounded by shells of normal matter and radiation at the distances the waves had reached. With each oscillation cycle, additional shells could form farther out. Then, after a few 100,000 years, the universe cooled enough for electrons and protons to combine into neutral hydrogen. In an instant, the photons were freed. Light could travel long distances without constant scattering. The pressure that had been supporting the acoustic waves vanished. The oscillations froze where they were, mid-motion. The clumps of dark matter remained at their origins. The shells of normal matter stayed at the radii the waves had reached at that moment. Over billions of years, gravity slowly amplified these patterns, drawing more material into both the central clumps and the shells. Galaxies formed more easily, where matter was already a little denser in the centers and along those frozen wave fronts. This process left a faint, beautiful fingerprint in the large-scale arrangement of galaxies. There is a slight preference for galaxy pairs to be separated by a particular distance. Pairs of galaxies are just a bit more common at a separation corresponding to the sound wave travel distance, stretched by cosmic expansion, than at separations that are slightly smaller or larger. This feature is called the baryon acoustic oscillation signal. The excess is small, only a few percent, but with surveys of millions of galaxies, it becomes clear, because we can calculate how far those waves would have traveled before they froze. Set by the physics of the early plasma, we know the original scale. We also know how much the universe has expanded since then, on average. That makes baryon acoustic oscillations a kind of cosmic ruler. By measuring how large that ruler appears at different distances and in different eras, we can track how the expansion of the universe has changed over time. Nearby, galaxies show the ruler at one apparent size. Galaxies far away, and thus seen in the past, show it at another. This method does not rely on Cepheids or supernovae. It rests on geometry and on well-understood early universe physics. That independence makes baryon acoustic oscillations a powerful cross-check, and it is here that the void's influence shows up in another, quieter way. Inside an underdense region, galaxies are not only receding because of expansion, they are also moving outward as part of the void's evacuation flow. That extra motion adds a bit of redshift on top of what expansion alone would cause. When we use that redshift to infer distances, the preferred separation scale between galaxies appears slightly stretched. The standard ruler looks a bit larger than it should. The size of this distortion depends on distance. For galaxies well within the void, the effect is strongest. For those beyond the void's outer edge, it fades away. By measuring baryon acoustic oscillations at many distances and comparing the apparent scale to what the early universe physics predicts, astronomers can map how strongly the local region is distorting the ruler. This is exactly what Indranil Banik set out to do. He and his collaborators gathered about 2 decades of baryon acoustic oscillation measurements from multiple surveys, optical and infrared, ground-based and space-based, and asked which model best fit the data: a nearly uniform universe, or one that includes a local void with properties similar to the KBC region. The result was striking. The void model fit the measurements around 100 million times better than the uniform model, what scientists would describe as a likelihood improvement of roughly 10 to the 8th power. And unlike distance ladders or pure cosmic microwave background analyses, this test relies purely on the geometry of galaxy clustering and on the physics of those ancient sound waves. In other words, baryon acoustic oscillations provide an independent check of the void hypothesis. They do not need Cepheids. They do not depend on supernova calibrations. They barely touch the cosmic microwave background, except through the well-established physics that sets the ruler's original length. And yet they, too, point toward the same quiet conclusion. We live in a region of space that is underdense, and that void gently but unmistakably shapes the measurements we make of the universe around us. To map something as vast as the universe, astronomers need a ruler that does not warp or fade with time. The baryon acoustic oscillation scale is exactly that, a measuring stick set in the early universe and carried forward, unchanged in its proportions. When atoms first formed, a few 100,000 years after the Big Bang, those ancient sound waves we talked about froze at a particular distance from their starting points. That distance, called the sound horizon, was on the order of a few 100,000 light years. Since then, space itself has stretched. The sound horizon has stretched with it. Today, that same pattern corresponds to roughly a few 100 million light years. The key is that everywhere in the universe, that frozen distance has been stretched by the same factor. The ratio between the original sound horizon and the size we see now tells us how much the universe has expanded. Measure that ratio at different cosmic times, and you start to sketch the history of expansion itself. Light from galaxies at modest redshift shows us the universe when it was younger, perhaps 2/3 of its current age. There, the baryon acoustic oscillation scale appears a bit smaller because less stretching has taken place between then and now. Galaxies at higher redshift show an even smaller apparent scale. Plot these measurements across time, and you get a gentle curve describing how expansion sped up or slowed down over billions of years. The elegance of this method lies in its simplicity. It does not rely on the intrinsic brightness of stars or the detailed physics of supernova explosions. Instead, it uses only where galaxies are in 3 dimensions and how often they appear at particular separations. When astronomers compute the correlation between galaxy positions, a small bump appears at the expected separation. That bump is the echo of the ancient sound waves, the baryon acoustic oscillation signal. To see it clearly, you need a lot of galaxies. With only a few tens of thousands, random noise can hide the bump. With millions, the pattern stands out. Modern surveys like the Sloan Digital Sky Survey, the Baryon Oscillation Spectroscopic Survey, and the Dark Energy Spectroscopic Instrument have mapped millions upon millions of galaxies, revealing the baryon acoustic oscillation ruler with beautiful clarity across a range of distances. There is, however, a wrinkle. To place galaxies at the correct distances, astronomers use redshift, how much their light has been stretched. That redshift has 2 parts. One part comes from cosmic expansion, the Hubble flow. The other comes from the galaxy's own motion through space, its peculiar velocity. A galaxy could have a certain redshift from expansion alone, but if it is also moving toward us or away from us, that motion adds to or subtracts from the total. On average, random peculiar velocities in random directions tend to cancel out when you look at enough galaxies. But not all motions are random. Sometimes whole regions of space share a coherent flow. A cluster might be streaming toward another cluster. A group of galaxies might be sliding out of a void. These bulk flows do not cancel. They subtly distort the baryon acoustic oscillation pattern, a phenomenon known as redshift space distortion. In a nearly uniform universe, matter flows inward toward density peaks, so the distortions follow a particular pattern. Clustering is squashed along the line of sight by infall motions. Inside a void, things flip. Matter flows outward instead, stretching the pattern in a different way. 2 decades of baryon acoustic oscillation measurements show hints of exactly these kinds of anisotropies near us. The pattern does not match perfectly what a strictly uniform lambda, cold, dark matter universe would predict. When researchers allow for a local underdense region resembling the KBC void, the distortions make more sense. By adjusting the void's radius, depth, and our position within it, they search for a model that best fits the data. The best fitting picture is one where the void has a radius of roughly 1 billion light-years, is about 1/5 less dense than average, and has Earth fairly near its center. That model does more than fit the baryon acoustic oscillation data. It naturally produces the magnitude of the Hubble tension, matches the observed bulk flows of galaxies, and aligns with direct galaxy counts that show a local underdensity. In that sense, the standard ruler method, completely independent of Cepheids, supernovae, and even most details of the cosmic microwave background, quietly points to the same conclusion. We live in a void, and that void bends our measurements just enough to make the universe look like it is expanding faster close by than it does on average. The explanation requires no new forces, no exotic particles, just standard cosmology applied with careful attention to local conditions. At high redshifts, far beyond the edges of our bubble, the baryon acoustic oscillation ruler measures the global expansion of the universe. At low redshifts, inside the void, it measures the locally modified expansion. Comparing the two reveals, in quantitative terms, how much the void is influencing what we see. Future projects will sharpen this picture. The Euclid space mission will map billions of galaxies over a large fraction of the sky. The Vera Rubin Observatory will scan the southern sky again and again, building deep catalogs of galaxies and their redshifts. Together, they will pin down the baryon acoustic oscillation scale to fractions of a percent at many cosmic epochs. If the void model is right, its properties will be measured with great precision. If it is not, the same data will show where it fails. One way or another, the ruler will give a clear answer. All of this happens within the broader framework of the lambda-cold dark matter model. The story cosmology has been refining for decades. With only a handful of key numbers, the present expansion rate, the densities of matter and dark energy, the overall shape of the initial fluctuations, and a couple of parameters describing their spectrum. This model describes the universe's evolution from a fraction of a second after the Big Bang to the present. It has passed test after test. It explains the pattern of temperature ripples in the cosmic microwave background, including subtle features like the third acoustic peak. It correctly predicts the relative abundances of light elements forged in the first minutes. It reproduces the large-scale clustering of galaxies and the pattern of gravitational lensing where mass bends light. It matches supernova observations that show the expansion of the universe accelerating under the influence of dark energy. For many years, every new observation seemed to fall gently into place within this picture. And then, two stubborn issues emerged: the Hubble tension and the KBC void. They are not tiny discrepancies at the edge of error bars. They challenge one of the model's quiet foundations. Lambda-cold dark matter assumes that, when you average over sufficiently large scales, the universe is homogeneous and isotropic, the same everywhere and in every direction. This assumption is known as the cosmological principle. It is the mathematical reflection of a philosophical lesson learned over centuries. We are not at the center of anything special. Earth is not central, the Sun is not central, the Milky Way is not central, and by extension, our patch of the universe should not be special either. Average the universe over a few 100 million light years, the principle says. And every region should look statistically similar. Same galaxy density, same distribution of matter, same expansion rate. The KBC void pushes against this. A region billions of light years across that is significantly underdense is larger than the scales where uniformity was expected to hold. Computer simulations built on lambda-cold dark matter start from realistic initial conditions and follow gravity as it pulls matter together over billions of years. They naturally produce a cosmic web with filaments, clusters, and voids. But the voids in these simulations are usually smaller, often a few 100 million light years in size. Once in a while, a larger one appears, but statistics suggest truly giant voids like the KBC region should be very rare. Depending on the details, some estimates say only 1 in 1,000 universes modeled this way would contain such a structure. Others say 1 in a million. And yet, here we seem to be. This is sometimes called a fine-tuning problem. Why do we find ourselves in such an improbable location? There are 3 broad ways to respond, none entirely comfortable. One is to shrug and say we are simply lucky. Rare things do happen. Someone wins the lottery. Despite very long odds, some planets end up with unusual orbits. Some regions of the universe happen to host enormous voids. We just happen to live in one. This answer is possible, but it leaves many with a quiet unease. A second option is to suspect that our simulations and our version of lambda-cold dark matter are not capturing everything. Perhaps the initial conditions were not quite as smooth as we assumed. Perhaps certain small-scale physical processes add up to make large structures more likely. Perhaps a mild adjustment to the amount or behavior of dark matter, or a brief phase of early dark energy, would allow bigger voids to form without breaking the successes of the model elsewhere. In this view, the framework survives, but with refinements. The third possibility is more radical. It suggests that the cosmological principle, at least in its simplest form, is not exactly true. Maybe the universe does not reach statistical uniformity on scales of a few 100 million light-years. Maybe you need to average over tens of billions of light-years larger than our entire observable universe to see the true smoothness. On the scales, we can actually observe significant variations in density and expansion might exist. We just happen to live in an underdense patch. This last idea is the hardest for many cosmologists to accept because it feels like a step back from the comforting notion that our vantage point is typical. But science is not obliged to preserve our comfort. If the data continue to say that a large void surrounds us and that its effects are real, we will have to weave that fact into our story of the universe, whether by refining lambda-cold dark matter, stretching the cosmological principle, or both. For now, the KBC void sits in the middle of that story, a vast, gently empty region that may resolve one long-standing tension, even as it opens a deeper question about how uniform the cosmos truly is, and how special, or not, our quiet little corner might be. It is a strangely comforting thought that Einstein might have been almost right, but not quite. General relativity has passed every test we have managed to throw at it for more than a century. It predicted gravitational waves, later heard by the detectors we call LIGO. It predicted the dark rings and glowing crescents around black holes, later imaged by the Event Horizon Telescope. It predicted how light bends around massive objects, something astronomers have confirmed thousands of times, and yet there is a catch that never quite goes away. To make our equations match what we see, we have had to add two invisible ingredients: dark matter and dark energy. Together they seem to dominate the universe, while everything we can see, stars, gas, dust, makes up only a small fraction. We have never directly detected dark matter or dark energy. We infer them because gravity appears to act as if extra mass and a strange negative pressure are present. So some physicists quietly ask, what if gravity itself changes character on the largest, faintest scales? What if the law is not wrong, but incomplete? One proposal along these lines is called modified Newtonian dynamics, often shortened to MOND. In this picture, gravity behaves exactly as Newton and Einstein described at the high accelerations we experience near planets and stars. But at extremely low accelerations, like those at the edges of galaxies or between galaxies, gravity becomes a little stronger than standard theory predicts. With that single change, a surprising number of galactic puzzles fall into place. Rotation curves of spiral galaxies, which stay flat much farther out than visible matter alone would allow, become natural without adding a vast halo of unseen dark matter. Dwarf galaxies behave as though their visible matter is enough. Tight, empirical relations between the amount of normal matter and the motions of stars emerge almost automatically. On the scale of individual galaxies, MOND has an uncanny knack for getting the right answer with very little freedom. Extending this success to the whole universe is harder. Clusters of galaxies still seem to require some form of unseen mass. Gravitational lensing observations, especially on large scales, resist being explained by modified gravity alone, The detailed pattern of the cosmic microwave background does not fall into line without additional ingredients. To address these issues, Pavel Krupa and colleagues have explored a cosmological version of MOND that includes neutrinos. In their model, the three familiar neutrino types are joined by a fourth, sterile neutrino, with a mass of about 11 electron volts. In combination with modified gravity at low accelerations, this extra neutrino population can reproduce many large-scale observations. Crucially, it tends to form large voids more readily than standard lambda cold dark matter does. In that framework, a structure like the KBC void is not a statistical freak. It is something that flows naturally from how structure grows. The cosmic web becomes more dramatic, emptier voids, denser filaments, sharper contrasts between regions. Our underdense neighborhood starts to look less surprising, but this version of the universe is not flawless either. Some measurements of galaxy clusters do not line up with its predictions. The parameter choices, like the exact neutrino mass, have to be tuned carefully for everything to work. Many physicists find it less economical than the standard picture in which dark matter is a simple, non-luminous particle and gravity keeps its familiar form. Occam's razor. The idea that we should prefer the simpler explanation when two describe the data equally well still nudges most cosmologists toward dark matter rather than modified gravity. Even so, the evidence for a large local void gives alternatives, like MOND, renewed attention. If lambda cold dark matter struggles to produce a void as big and deep as the KBC region, while modified gravity does so naturally, then perhaps the void is quietly pointing toward new physics. If the Hubble tension remains even after we account carefully for the void's influence, changes to gravity might explain the leftover discrepancy. For now, the debate stays open. Some recent analyses favor standard cosmology plus a void. Others see hints that modified theories perform better. The data is still too soft and noisy to close the case. While these battles play out, another question sits in the background, simple to ask and subtle to answer. How old is everything? Under the standard lambda cold dark matter model, reading the cosmic microwave background and folding in a Hubble constant around 67 kilometers per second per megaparsec gives a cosmic age of about 13.8 billion years. The ripples in the microwave sky encode how long the universe has been expanding and cooling, and the age drops straight out of the equations. If you instead take the locally measured Hubble constant near 73 kilometers per second per megaparsec and treat it as the universal value, the story changes. A faster expansion to reach the same present size means less time has passed. The resulting age is closer to 13.0 billion years. The difference, around 800 million years, is not trivial. That is enough time for several full generations of stars to live and die. Enough time for galaxies to collide and merge. Enough time to reshape the timeline of structure formation. So which age is right? The answer may again depend on what exactly we are measuring. If we live inside a region where expansion runs slightly faster than average, then a clock that tracks only our local flow might suggest a younger age, something like 13 billion years, while a clock that averages over the whole universe still reads 13.8 billion years. Two ages, two perspectives, not necessarily contradictory. This would be fine if all the oldest objects in the universe fit comfortably below the lower age, but some of the oldest stars we have dated, especially those in ancient globular clusters, seem to come in around 13.2 billion years. with radioactive dating of heavy elements giving similar numbers. Ages carry uncertainties. Stellar models and nuclear decay rates are not perfect. Those uncertainties might allow us to nudge the oldest stars down a little, perhaps to 12.8 billion years or so. Still, it would be unsettling if the universe as a whole were younger than some of its residents. One gentle way out is to keep the global age anchored by the cosmic microwave background at about 13.8 billion years, and to treat the higher local expansion rate as a quirk of our neighborhood that does not change universe's true age, only our inference of it. In that case, stars older than 13 billion years pose no problem, and the void explains the Hubble tension without forcing us to shorten the cosmic timeline. Another, more speculative possibility is to recognize that in general relativity, time does not flow identically everywhere. Strong gravitational fields slow clocks. Deep in a gravitational well, time passes a little more slowly than in emptier space. In principle, integrated over billions of years, such differences might build up into small offsets in effective age between regions. Matter, sitting in the deep potential of dense clusters, could, in a sense, experience slightly less proper time than matter drifting in a void where gravity is weaker and clocks tick a bit faster. In practice, these effects are probably too small to solve the Hubble tension outright. But they are a reminder that the age of the universe is not a simple, one-size number. It depends on the model you assume and on how you average the different paths that time can take. Change the model, and the age shifts a little. To see how all of this ties back to our void, it helps to imagine what the universe looks like when you stop thinking of it as a static picture and start seeing it as motion. Galaxies do not just sit on a frozen web. They flow across hundreds of millions of light years. Vast streams of matter drift together, like rivers etched into space-time. These are bulk flows, coherent motions, too large to be bound within a single cluster, extending from voids to superclusters. In the standard picture, such flows should fade as you look on larger and larger scales. Random, peculiar velocities average out, and expansion dominates. Beyond a few 100 million light years, the model predicts that bulk flows should be modest, on the order of perhaps 100 kilometers per second at 300 million light years, and even smaller beyond. Observations tell a slightly noisier story. Multiple studies find bulk flows of 400 kilometers per second or more on scales of several 100 million light years. Some analyses hint at velocities even higher. These flows point toward massive structures such as the Shapley supercluster, a huge concentration of galaxies, roughly 650 million light years away, whose gravity tugs on matter across enormous distances. Closer to home, we see the signature of void evacuation. Galaxies in and near the local void move outward at speeds of a few hundred kilometers per second. On larger scales, the KBC void adds its own pattern. Galaxies within roughly a billion light years of its center participate in an outward drift. Near the center, the flow is slower. The gravitational gradient is gentle there. At intermediate radii, the outward speed is greatest, where the pull from surrounding walls is strongest, but galaxies have not yet crossed into denser territory. Near the outer edge, local gravity from clusters tempers the motion again. This layered velocity profile matches what is measured in catalogs like cosmic flows, which track peculiar velocities for tens of thousands of galaxies. The way the speed varies with distance, the directions of the flows, and their magnitudes all line up well with a large underdensity in our region. For some researchers, the flows are still a touch too strong for standard lambda-cold dark matter, even when voids are included. That pushes them toward modified gravity, where matter responds more strongly to density contrasts, and fast flows arise more naturally. Others argue that tweaks to the initial fluctuation spectrum or to small-scale physics may be enough within standard cosmology. Whatever the deeper explanation turns out to be, one practical point is clear. These cosmic rivers affect how we read the universe's expansion. Every time we measure a galaxy's redshift, we are seeing the sum of two things: the stretching of space itself and the galaxy's own peculiar motion. If that galaxy is swimming along a bulk flow toward us, its redshift is reduced. If it is being carried away from us, its redshift is increased. For small, random motions, these effects blur together and mostly cancel when we average over lots of galaxies. But a coherent flow that moves many galaxies in similar directions leaves a statistical imprint. The evacuation of the KBC void is just such a flow. In most directions on our sky, galaxies are sliding away from us as they roll down the gravitational hill of the void toward denser regions. That outward motion quietly adds to the redshift we measure on top of the redshift from cosmic expansion. If we do not account for it perfectly, we will infer an expansion rate that is a little too high. In that sense, the rivers of galaxies draining our local void are not just a curiosity of cosmic weather. They are another way in which our underdense neighborhood tilts the scales, making the local Hubble constant appear larger than the true cosmic average. To correct for these great rivers of galaxies, astronomers need to know the velocity field around us in careful detail. Right now, they use models built from the observed distribution of galaxies, where matter is dense, where it is sparse, how filaments and clusters pull. Those models predict bulk flows, and those predicted motions are subtracted from the redshifts we measure. But if the models are incomplete, if a large underdense bubble like the KBC void is left out or misjudged, then a residue remains. A quiet bias survives in the data. The void must be woven into these flow models. Ignoring it means predicting the wrong currents, applying imperfect corrections, and letting some of the void's influence leak into our inferred expansion rate. When the void is included, different ways of measuring the Hubble constant begin to sit more comfortably together. If you step back far enough, the universe looks a little like foam frozen in mid-motion. Bright filaments of galaxies trace the thin walls of bubbles. Clusters gather where several filaments intersect, like knots where many soap films meet. Inside the bubbles lie the voids, the great, low-density interiors. This cosmic web did not fit the early intuition of many cosmologists. In the 1970s, before the first wide three-dimensional surveys, it was common to imagine galaxies sprinkled more or less evenly through space. Then, larger redshift maps arrived, and the picture changed abruptly. The first maps showed long, delicate threads of galaxies stretching for hundreds of millions of light-years, and enormous dark regions in between. Later, the Sloan Digital Sky Survey revealed the pattern in extraordinary detail, and the foam analogy became hard to ignore. Statistically, most of the volume of the universe belongs to voids. By simple density criteria, perhaps 4/5 of all space counts as underdense, and only about 1/5 as relatively dense. Yet most of the galaxies live in that smaller, denser fraction. Something like 4/5 of them gather in filaments and clusters, leaving only a minority scattered through the emptier regions. That degree of contrast does not arise from gentle gravity acting on perfectly mild fluctuations. Dark matter helps sharpen the pattern. It does not feel radiation pressure. So in the early universe, it could begin collapsing into clumps before normal matter could. Later, gas fell into those dark halos, amplifying the difference between dense and empty areas. Time also matters. Gravity has had more than 13 billion years to exaggerate small differences into big ones. Dense places pull in more matter and grow denser still. Thin places lose their matter and grow thinner. Dark energy contributes in its own quiet way. By accelerating the expansion of space, it allows voids to widen faster than matter can fall back in. In a universe without dark energy, some voids might eventually have been partly refilled by surrounding material. In our universe, acceleration stretches them so quickly that they become more and more evacuated. All of this is dynamic, not static. Filaments slowly shift, clusters merge, and voids expand. Galaxies slide along filaments like cars following highways at night, drawn toward the gravitational lights of clusters where filaments intersect. Some are captured there, others continue through, flowing out toward other nodes. Voids nudge matter outward along pressure and gravity gradients. The cosmic web channels motion into organized streams rather than random wandering. Our own place in this web matters. The Milky Way belongs to a flattened structure called the local sheet, a thin filament that forms one boundary of the nearby local void. On one side lie relatively empty regions. On the other loom denser structures like the Virgo cluster and the distant Shapley supercluster. Beyond all of that, the KBC void wraps around on much larger scales. We live in a balance of pulls and pushes, with the void easing us outward and massive clusters tugging from afar. This environment imprints itself onto everything we observe. The uneven richness of galaxy fields in different directions. Slight warm and cool patches in the cosmic microwave background that trace nearby structures, the patterns of bulk flow that show up in catalogs of galaxy velocities. None of these are mistakes. They are the signature of the web we inhabit. Because of that, mapping the web precisely has become one of cosmology's quiet priorities. The sizes and shapes of voids and filaments, how they connect, how massive they are, these all test our theory of structure formation. For the most part, simulated universes grown under lambda, cold dark matter physics, yield webs that look statistically similar to what we see, but on the extremes, the largest known voids and the richest superclusters edge beyond what simulations typically produce. The KBC void and the Shapley region sit out near those edges, daring us to be sure of our models. The same web shows us where dark matter must be, because light bending and galaxy clustering follow the same skeleton. Dense nodes and filaments hide invisible mass. Voids, by contrast, are thin not only in stars, but in dark matter as well. Future surveys, with deeper catalogs and more precise lensing maps, will outline this skeleton with far greater clarity. Against this backdrop, the KBC void stands as both an explanation and a question. It offers a graceful way to understand the Hubble tension and matches several independent lines of evidence: bulk flows, galaxy counts, baryon acoustic oscillation distortions. But to move from plausible to decisive, astronomy will need more than a suggestive picture. It will need tests that either gently confirm the void's role or politely push it aside. One such test is straightforward in concept. We can measure the Hubble constant using galaxies and supernovae that are well beyond the void's edge, at distances of a few billion light-years. If the void is what inflates our local value, then measurements that mostly sample space outside it should lean back toward the lower expansion rate inferred from the cosmic microwave background. If they stubbornly stay high, something else must be going on. The James Webb Space Telescope, with its sensitivity to faint Cepheid variables in distant galaxies, is already helping extend the distance ladder in this direction. Another test is to map the void's three-dimensional shape with much finer detail. We know we live in an underdense region, but the precise boundaries, the exact depth, and the true center remain fuzzy. The Vera Rubin Observatory, repeatedly imaging the southern sky and building a catalog of billions of galaxies, will sharpen that picture enormously. If the KBC void exists, as the models suggest, it should appear as a broad, fairly smooth underdensity, with Earth lying not too far from its middle. If the data instead reveal a patchwork of smaller voids and dense walls with no coherent bubble, the hypothesis will have to bend or break. A third line of evidence comes from bulk flows at multiple distances. Projects like cosmic flows are steadily improving our map of peculiar velocities, and future space missions such as the Nancy Grace Roman Space Telescope will add even more distant galaxies to the chart. The pattern of velocities should show galaxies streaming outward from the void center, with speeds and directions lining up with the underdensity seen in galaxy counts. If those flows match predictions, confidence in the void model will grow. If they do not, we will learn something equally important. A fourth possible signature lies imprinted on the cosmic microwave background itself through what is called the integrated Sachs-Wolf effect. As photons from the microwave background cross evolving gravitational landscapes, they gain or lose a tiny bit of energy. Passing through a large void that is becoming emptier over time should leave a subtle cold spot, a whisper of extra redshift. Some current maps from the Planck satellite hint at such a feature roughly where the KBC void would be, but the signal is weak and noisy. Future experiments with finer sensitivity could clarify whether that hint is real. Fifth, baryon acoustic oscillation measurements at different distances can be compared carefully. Inside the void, the standard ruler is nudged by evacuation flows. Outside, it should reflect the global expansion more cleanly. Missions like Euclid and instruments like the Dark Energy Spectroscopic Instrument are gathering precisely the kind of data needed to see whether the ruler behaves differently within and beyond our suspected bubble. Finally, astronomers can search for other large voids and ask a simple but profound question: are we alone in this kind of environment? If similar underdense bubbles are found elsewhere, each with its own small Hubble tension from the viewpoint of hypothetical observers living there, then voids become a natural part of the landscape rather than an oddity. If ours is truly unique within the volumes we can survey, the pressure on standard cosmology increases. Many of these projects are already underway. Over the next decade or so, the sky will quietly return an enormous harvest of data, deeper maps of galaxy positions, sharper measurements of their motions, better readings of the microwave background, more precise standard rulers and candles. By the time that harvest is complete, the KBC void hypothesis will have faced every test we know how to give it. It may emerge intact, a simple and beautiful explanation for a long-standing puzzle. Or it may fray at the edges, forcing us to admit that local structure alone cannot account for the Hubble tension, and that new physics waits behind the next corner. Either way, we will not be left in the dark. We will have learned more about the shape of the web we inhabit, the currents that carry our galaxy through space, and the ways in which our special little patch of the cosmos differs from the average. The waiting, in its own way, is part of the wonder. The evidence is already strong enough to be enticing, but not yet heavy enough to be final. That lingering uncertainty, that quiet pause before the answer settles, is not a failure of science. It is the feeling of science doing exactly what it should, holding its breath beside us in the dark, listening carefully, and letting the universe finish its sentence. Dark energy sits in the background of everything, like a quiet pressure you cannot feel but that never stops working. By our best estimates, it makes up about 68% of all the mass and energy in the universe. It is the reason expansion is not slowing down under gravity's pull, but gently speeding up. In the standard story, without dark energy, gravity would gradually win, galaxies would tug on one another, the expansion would slow, and in some models the universe might even turn around and collapse. Dark energy keeps that from happening. It pushes space apart. In the lambda cold dark matter picture, dark energy is not a complicated substance. It is Einstein's cosmological constant, a constant energy density that fills space uniformly, like a very faint tension in the vacuum. As space grows, there is more vacuum, and therefore more of this energy. More dark energy means stronger push. Stronger push means faster expansion. Faster expansion means more space. The cycle feeds itself, leading to a slow runaway that continues forever. This very simple description fits a great deal of what we see: distances to supernovae, the ripples in the cosmic microwave background, and the way structure grows on large scales all line up nicely if dark energy behaves like a constant vacuum energy with just the right strength. And yet, just beneath that smooth surface, the familiar tensions remain. There is the Hubble tension, the mismatch between local and global expansion rate, and there are hints from some recent spectroscopic surveys that dark energy might not be perfectly constant in time. Observers describe dark energy using an equation of state parameter, usually called W. A value of -1 corresponds to a true cosmological constant. Values that differ from -1, even a little, suggest that dark energy might evolve. Some early results have whispered that W could be ever so slightly different from -1, close enough to be uncertain, but far enough to tug at the imagination. If that were confirmed, dark energy would not be a fixed property of the vacuum. It would behave more like a field that slowly rolls or shifts over cosmic time, something like the quintessence fields that appear in some particle physics ideas. In those models, the energy density of the field can change as it moves along a potential landscape, giving more flexibility than a simple constant. But every time theorists try to use time-varying dark energy to solve the Hubble tension, new problems appear. Raising the early expansion rate enough to match local measurements tends to disturb other parts of the cosmic story. Galaxies form too quickly or too slowly. Galaxy clusters do not show up in the right numbers. Peaks in the microwave background power spectrum shift to the wrong places. No simple, dynamical dark energy model has yet fixed the Hubble tension without breaking something else. The void offers a gentler possibility. Perhaps dark energy really is constant everywhere, exactly as Einstein's cosmological constant suggests. Perhaps the apparent differences we infer from different methods do not come from dark energy changing, but from the environments in which we measure it. Inside a void, matter is sparse and gravity is weaker. The same dark energy competes against less mass, so its push is more obvious. Expansion can accelerate more freely. Inside a massive cluster, matter is dense and gravity is strong. There, dark energy's effect is partially counterbalanced, and expansion is more tightly restrained. An observer in a void and an observer in a cluster could each measure an effective dark energy strength, and those values would differ, even though the underlying cosmological constant is the same. It is a bit like measuring wind. The large-scale atmosphere may have a certain wind speed at high altitude, but at ground level, trees, buildings, and hills shape what you actually feel. One person standing in a sheltered valley feels a gentle breeze. Another on a ridge feels a strong gust. Both are right for where they stand. But neither reading alone gives the global picture. In the same way, measuring expansion from inside a large void gives you the expansion rate as it behaves there. It does not directly represent the universal average. The cosmic microwave background, by contrast, samples the entire sky and effectively averages over the whole observable universe. It is that global average which reveals the true strength of dark energy. Local measurements, especially those taken inside a special region like the KBC void, must be interpreted with that context in mind. If this view is correct, we can keep the cosmological constant intact. Dark energy remains a simple, uniform vacuum energy, constant in time and space. The seeming contradictions are not telling us that dark energy is different in different eras. They are telling us that the universe is structured and that our vantage point is not generic. That does not make dark energy any less mysterious. Even if it is a perfect cosmological constant, we still do not know what it is. Calculations from quantum field theory, when naively applied, suggest that vacuum energy should be unimaginably larger than what we observe. So much larger that the discrepancy is sometimes called the worst prediction in physics. Quintessence-like fields can soften that problem by allowing the energy density to evolve, but they introduce new questions and free parameters of their own. Some researchers have wondered whether dark energy might be an illusion, a misinterpretation born of living in a structured universe. In models where voids are very large and expansion differs strongly from place to place, it is possible to mimic the appearance of acceleration without introducing a true dark energy component. But when all data are considered together, the microwave background, cluster counts, baryon acoustic oscillations, supernovae, the no dark energy options, struggle. The universe seems to demand some form of dark energy to make sense as a whole. The void colors how we measure it, but does not erase its need. Future observations will help untangle these threads. Measurements of expansion well beyond the edges of our local bubble will show whether the effective dark energy strength truly appears different from place to place. Detailed maps of void growth and cluster abundance will reveal how dark energy and large-scale structure interact. Comparisons between independent methods, distance ladders, standard rulers, gravitational lensing, and microwave background analyses will show whether contradictions remain once local environment is fully accounted for. Through all of this, dark energy stays at the center of cosmology's deepest questions. The void hypothesis does not close that chapter, but it reminds us to be careful. When your laboratory is a single patch of the universe, knowing the peculiarities of that patch is not optional. It is part of the measurement. The lesson that emerges is quietly humbling. We are not in a typical place. Our surroundings do not represent an average slice of the cosmos. The numbers we extract, expansion rates, matter densities, effective dark energy strengths, are colored by the fact that we live inside an underdense bubble drifting through the cosmic web. For a century, ever since Edwin Hubble first noticed that distant galaxies recede faster the farther away they are, astronomers have tended to assume that the behavior we measure nearby reflects the behavior everywhere. Hubble's law was taken to be universal, with a single Hubble constant describing the link between distance and recession speed across all of space. The KBC void suggests the reality is more nuanced. The relationship between distance and velocity still holds, but the proportionality can depend slightly on where you stand. Inside a void, the expansion rate you infer is a bit higher. Inside a cluster, a bit lower. Average over everything, and you recover the global Hubble parameter. Measure only your local neighborhood, and you get something more parochial. Why did we cling so strongly to the idea of uniformity? Partly because it felt like the natural extension of the Copernican lesson. Earth is not the center. The Sun is not special. The Milky Way is one among many. It was tempting to add, almost automatically, that our particular patch of the universe cannot be special either. Partly because, on a practical level, assuming uniformity turns Einstein's formidable equations into something we can actually solve. Homogeneous models make cosmology possible as a working science. But assumptions, no matter how elegant, must ultimately bow to observation. The large voids and rich superclusters we see tell us that real space is lumpier on very large scales than the purest form of the cosmological principle suggests. Uniformity still holds as a good approximation when you smooth over enormous distances, but it may require averaging over volumes larger than our own observable patch. That recognition has several consequences. We have to be explicit about which expansion rate we mean, local or global, when we quote a Hubble constant. We have to map our environment carefully, rather than assuming away its peculiarities. We have to consider that our location might be statistically unusual, and then ask whether that is simply a roll of the cosmic dice, or a clue that voids are more common or more hospitable than we thought. Most of all, we are reminded that every theory, no matter how successful, is provisional. Newton's gravity worked beautifully until experiments and observations reached regimes where its limits showed. Einstein's relativity extended and refined it. Lambda cold dark matter has carried cosmology through decades of remarkable progress, but now we see where its assumptions are being stressed by a local expansion rate, by a giant void, by the subtle structure of the cosmic web. The KBC void is part of that new boundary. It tells us that our cosmic address matters, that local structure can tilt our measurements, that the universe is even more textured than our cleanest equations suggest. Whether accounting for this bubble fully resolves the Hubble tension, or whether deeper changes to our models will be needed, is a story still unfolding. What we know for now is that we live inside a vast, gently empty region, roughly 2 billion light-years across, and that this quiet hollowness touches everything we infer about the cosmos. Beyond its edge, the universe expands at something closer to its true average pace, indifferent to our special vantage point. Out here, on our small world inside this great bubble, we watch, we listen, and we try to reconstruct the whole from our one fragile perspective. The data keeps arriving, the questions keep deepening, and the universe, calm, patient, and unhurried, waits for us to piece together what it has been doing all along.